My name is Deborah Kitzler, and this is my lab report for the fourth lab in Physics 2211. This lab dealt with oscillating motion. So we were given a video and we were told to track and then predict the motion of an oscillating object when it was on a vertical spring. First, we utilized the program tracker to obtain position data from this object given the video that we were provided. We then went into GlowScript and created a code that would produce a model of an object oscillating on a vertical spring, and this is our predicted data. We use the assumptions that the total energy of our system was conserved, meaning that the total change in energy, or delta E, would equal 0. And then we said that 3 energies contributed to this total energy: kinetic energy, gravitational potential, and spring potential. And our job was to compute the kinetic, the gravitational potential, and the spring potential such that the total energy of the system was conserved. The principles used throughout this lab are the momentum principle. We use this to create iterative calculations in our GlowScript to produce the velocities and the position of the object over time. We also use the conservation of energy, which states that the total change in energy is equal to the work done on the system plus Q. However, Q was not used in this lab. It was said to be equal to 0. And we also were working with a vertical spring, so the work done on the system, which is equal to the total change in energy, is equal to the change in kinetic energy, the change in spring potential energy, and the change in gravitational potential energy. And you can see how these were calculated below, and this is the equation for each of these. However, you will see that they are written slightly different later on in the GlowScript code. This is a small screenshot from the tracker program. You can see that we tracked the center of mass of our object as it oscillated on a vertical spring to obtain positions in the X and the Y directions. This is the beginning of the GlowScript code. You can see that the initial conditions is the mass of the object was 0.402 kilograms. The initial position, which we obtained from tracker, were negative 0.115 on the X direction and negative 0.625 on the Y direction. And this is when the top of the spring is put at the origin and the ball hanging straight down on the spring, or the object hanging straight down on the spring, is along the Y axis. We also assumed that the initial velocity was 0 as the object was dropped. You can see in the highlighted portion of this GlowScript code the 3 equations used to calculate kinetic, spring potential, and gravitational potential energy. So you can see that the kinetic energy is 1/2 the mass times the velocity squared. The spring potential is 1/2 the spring constant times the S squared, which is the length that the spring has been extended past its original length. And then you can see that the gravitational potential is the mass times gravitational constant, 9.8, times the position of the ball. Now you can see how the net forces acting on the object are the gravity and the spring, and these add up to be the net force. We use this net force to calculate the new velocity and this velocity to calculate the new position in an iterative format. We then updated our position and the kinetic energy of the object, which created a new L, or how far the spring had been extended, and then calculated the changes in energies and updated our graphs before going back to the beginning and continuing this process over until the time was complete. Now this produced results from our GlowScript. Here you can see the change in energy versus time. The delta E, or the total change in energy, is 0, which indicated that the energy of our system was conserved. You can also see that the energy of the spring and the energy of gravity, or the spring potential, gravity potential, they always acted in opposite directions, which does make sense. Then we can also see that the change in kinetic energy reflected the oscillating motion such that it decreased in magnitude before increasing in magnitude. Now we can compare the positions versus time, the observed versus expected. In both the X and the Y, you will see they are very, very close in the beginning. However, they differ more as time goes on. This could be perhaps due to human error, or also other external factors such as air resistance or drag that were not accounted for. Again, you can compare and see. However, one more small difference you can see in the Y versus the X is that the observed Y positions are generally smaller than the expected Y positions. And this could also be due to an inaccurate spring constant, or which would lead to an inaccurate calculation of the stretch of the spring. What does this mean? Now, does our model account for the energy principle? Yes, because the total change in our energy of the system is 0, which was reflected in the orange line on the graph, which stated that the total change in energy of the system was constantly at 0. Therefore, the energy principle is satisfied. Also, we can see the two different periods. So the period based on X was approximately 1.6 seconds, whereas the period based on Y was approximately 1.5. Now, this could be due to that there are more forces acting in the Y direction, the gravity and the spring, as opposed to just the spring and the X. And now this resulted in a slightly smaller period when we used the Y position versus time to calculate it. Thank you.